Welcome back, everyone. In this season, we will develop the axiomatic foundations of probability theory. In our lives, and especially in science and technology, we often try to minimize the risk, get rid of any uncertainty. But in probability theory, we take a radical stance. We actually make uncertainty the object of our study. But how is it even possible to do that? Isn't science and math all deterministic as opposed to random? Doesn't 2 + 2 always equal 4 and not probably 4, but maybe 5? Enabling our study of probability within science, making probability theory a rigorous part of mathematics, was one of the biggest intellectual feats of the 20th century. Today, we start to learn these mathematical foundations of probability. There will be terminology. It is important that you learn this terminology now and you learn it well. So please pay special attention to this and the next couple of episodes. Here's our first definition toward the rigorous understanding of probability. Consider conducting some experiment. The experiment can result in one or more outcomes. The set of all possible outcomes is called the sample space. Subsets of the sample space that we denote S are called events. Don't worry, we'll give a lot of examples about this definition. It will be clear what we exactly mean. We can visualize the sample space using the Venn diagram. Imagine S as being this universe denoted by the square. An outcome can be any point, and an event is a subset, such as this one. Looking a little bit forward, probability will be a number between 0 and 1 that will be assigned to each event. But for now, we just need to remember these technical terms: experiment, outcome, sample space, and events. And as promised, lots of examples. First, consider just flipping a coin twice. Our experiment will be to flip a fair coin twice. There are 4 possible outcomes. HH will denote the outcome where the coin comes up head twice. It can also be a head and a tail and a head, tail and tail. These are all 4 possible outcomes of our experiment. The set of these outcomes, the list of them, that we will denote with curved braces like this, is the sample space. There are various events that we may be interested in. For instance, an event could be getting ahead once. This event consists of 2 outcomes, HT and TH. Here's our second example. Imagine that the experiment consists of recording the time of the first 911 call at a police station today. The set of all possible outcomes is the set of all possible times of the call between midnight, which we'll denote by 0, and the next midnight, which we denote by 24 hours. A possible event could be that someone calls by 9 a.m., in which case the event is just the interval between 0 and 9. So our sample space is between 0 and 24, and an event, E, is a subset from 0 to 9. Another experiment Consider tossing 2 dice. Here an outcome is just a pair of numbers. The set of all possible outcomes is just the set of all pairs of numbers between 1 and 6. How many outcomes does the sample space have? Well, by the multiplication principle, it's 6 ways to choose the first number, and for each selection of the first number, there are 6 ways to choose the second number, so that it's 36. An example of an event as a subset of S could be where the sum of the 2 dice is at least 10. Explicitly, we can write this as a set of all these outcomes. 4, 6 is a good outcome, right? 5, 5 is a good one. 5, 6, the sum in this case is 11. 6, 4, 6, 5, and 6, 6. These are all the pairs whose sum is at least 10. They constitute this event E. Example 4. Here our experiment is a study on families, where we record the sex of the children, starting from the older child. What are the possible outcomes of this experiment? First of all, the family may have no children. Let's denote this by N, no children. Then, if a family has 1 child, it could be either a boy or a girl. If the family has 2 children, it could be 2 boys. Boy older, girl younger. Girl younger, boy. Girl older, boy younger. Both girls. The family may have 3 children. In this case, it could be all boys, boys first, and the girl is the youngest, and so on and so forth. These are all possible outcomes of this experiment, and there are infinitely many. In this case, the sample space has infinite size. One possible event that we may be interested in is that the older child is a boy. And that event is a subset of S, and it consists of the following outcomes. Just 1 boy in the family, or 2 boys, a boy and a girl, boy older, 3 boys, boy, boy, and girl, and so on. It is an infinite set. And one more example. Here our experiment is to choose 10 rats from a lab that has 100 rats. In this case, an outcome is just any selection of 10 rats from 100 rats. So the sample space consists of all possible selections, all possible subsets of 10 rats from this lab. How large is the sample space? How many ways are there to select 10 rats out of 100? That's 100, choose 10. Suppose in this lab, 40 rats are sick and 60 are healthy. A possible event that we may be interested in is that the sample be representative. In other words, the sample has 4 sick and 6 healthy rats. More explicitly, this event consists of all subsets of 10 rats with an additional requirement that the subset must have 4 sick and 6 healthy rats. What is the size of E? How many outcomes does E have? We have to choose 4 sick rats from the 40 sick. For any such selection, we then select 6 healthy from 60 healthy. And so we multiply that. Stay with me for the next episode.